Hello everyone, I am Sunil Kumar BL, Associate Professor, Department of Computer Science and Engineering, Canara Engineering College. I am handling Advanced Computer Architectures 17 CS 72. Textbook is Advanced Computer Architecture by Kai Hong and Naresh Jotwani. Reference book is Computer Architecture, a Quantitative Approach by John L. NSC and David A. Patterson. Chapter 12 Instruction Level Parallelism. Reorder Buffer. Since instructions execute in parallel on multiple functional units, the reorder buffer serves the function of bringing complete instruction back into an order which is consistent with the program order. Note that instruction may complete in an order which is not related to the program order, but must be committed in the program order. At any time, program state and processor state are defined in terms of instructions which have been committed, that is, their results are reflected in appropriate register and/or memory locations. The concept of program state and processor state are important in supporting context switches and in providing precise exceptions. Entries in the reorder buffer are completed instructions which are queued in program order. However, since instructions do not necessarily complete in program order, we also need a flag with each reorder buffer entry to indicate whether the instruction in that position has completed. Figure shows a reorder buffer of size 8. 4 fields are shown with each entry in the reorder buffer: instruction identifier, value computed, program specified destination of the value computed, and a flag indicating whether the instruction has completed. The figure also shows the head of queue of instructions arbitrarily labeled in instruction of I. This is the instruction which would be committed next if it has completed execution. When this instruction commits, its resultant value is copied to its destination, and the instruction is then removed from the reorder buffer. The next instruction to be issued in the issue stage of the instruction pipeline then joins the reorder buffer at its tail. If the instruction at the end of the queue has not completed and reorder buffer is full, then further issue of instruction is held up. That is, pipeline stalls because there is no free space in the reorder buffer for one more entry. The result value of any other instruction lower down in the reorder buffer, say value of I plus k, can also be used as an input operand for a subsequent operation, provided of course that the instruction has completed and therefore its result value is available, as indicated by the corresponding flag ready of I plus k. In this sense, we see that the technique of operand forwarding can be combined with the concept of reorder buffer. It should be noted here that operands at the input latch of functional unit as well as values stored in the reorder buffer on behalf of completed but uncommitted instructions are simply work in progress. These values are not reflected in the state of the program or processor as needed for a context switch or for exception handling. We can discuss how the use of reorder buffer addresses the various types of dependencies in the program. 1. Data dependencies. A raw dependence, that is, true data dependence, will hold up the execution of the dependent instruction if the result value required as its input operand is not available. As suggested above, operand forwarding can be added to this scheme to speed up the supply of the needed input operand as soon as its value has been computed. WAR and WAW dependencies, that is, anti-dependency and output dependency, respectively, also hold up the execution of the dependent instruction and create a possible pipeline stall. We shall see below that technique of register renaming is needed to avoid the adverse impact of these two types of dependencies. Second one, control dependencies. Suppose the instruction in the reorder buffer belong to a branch in the program which should not have been taken. That is, there has been a mispredicted branch. Clearly, then the reorder buffer should be flushed along with other elements of the pipeline. Therefore, the performance impact of the control dependencies in the running program is determined by the accuracy of branch prediction technique employed. The reorder buffer plays no direct role in the handling of control dependencies. Third, resource dependencies. If an instruction needs a functional unit to execute, but the unit is not free, then instruction must wait for the wait unit to become free. Clearly, no technique in world can change that. In such cases, the processor designer can aim to achieve at least this. If a subsequent instruction needs to use another functional unit which is free, then subsequent instruction can be executed out of order. Register renaming. Traditional compilers allocate registers to program variables in such a way as to reduce the main memory access required in the running program. In programming language C, in fact, programmers can even pass a hint to the compiler that a variable be maintained in a processor register. Traditional compilers and assembly language programmers work with a fairly small number of programmable registers. The number of programmable registers provided on a processor is determined by either 1. The need to maintain backward instruction compatibility with other members of the processor family, or second one, the need to achieve reasonably compact instruction encoding in binary with 16 programmable registers. For example, 4 bits are needed for each register specified in the machine instruction. The only way to make a large number of registers available to instructions under execution within the processor is to make the additional registers invisible to machine language instructions. Instructions under execution would use these additional registers even if instruction making up the machine language program stored in memory cannot refer to them. example, let's say that the instruction f add r1, r2, r5 is followed by the instruction f sub r3, r4, r5. Both these instructions are writing to register R5, creating thereby a WAW dependence, that is, output dependence, on register R5. Clearly, any subsequent instruction should read the value written into R5 by F sub and not the value written by F add. Figure shows this dependence in graphical notation. With additional registers available for use as these instructions execute, we have a simple technique to remove this output dependence. Let F sub write its output value to a register other than R5 and let us call that other register X. Then instructions which use value generated by F sub will refer to X, while instruction which use the value generated by F add will continue to refer to R5. Now since F add and F sub are writing to two different registers, the output dependence or WAW between them has been removed. When F sub commits, then the value in R5 should be updated by the value in X, that is, the value computed by F sub. Then the physical register X, which is not in a program visible register, can be freed up for use in another such situation. Note that here we have mapped or renamed R5 to X for the purpose of storing the result of F sub and thereby removed the WAW dependence from the instruction stream. A pipeline stall will not be created due to the WAW dependence. In general, let us assume that instruction ij writes a value into register rk. At the time of instruction issue, we map this programmable register rk onto a program invisible register xm, so that when instruction ij executes, the result is written into xm rather than rk. In this program, invisible register xm, the result value is available to any other instruction which is truly data dependent on ij, that is, which has read after write dependence on ij. If any instruction other than ij is also writing into rk, then that instance of Rk will be mapped into some other program invisible register Xn. This renaming resolves the WAW dependence between the two instructions involving Rk. When instruction ij commits, the value in xm is copied back to rk and the program invisible register xm is freed up for reuse by another instruction. A similar argument applies if ij is reading the value in rk and a subsequent instruction is writing into rk, that is, there is a WAR dependence between them. The technique outlined, which can resolve WAR and WAW dependencies, is also known as register renaming. Both these dependencies are caused by a subsequent instruction writing into a register being used by a previous instruction. Such dependencies do not reflect program logic but rather the use of a limited number of registers. Let us consider the instructions f add R6, R7, R2, f add R2, R3, R5 are followed later in the program by the instruction f serve R1, R3, R2. The first f add instruction is writing a value into R2, which the second f add instruction is being used. That is, there is true data dependence between these two instructions. Let us assume that when the first fadd instruction executes, R2 is mapped into program invisible register XM. The later fserve instruction is writing another value into R2. Clearly, the second fadd should see the value in R2 which is written by the first fadd and not the value written by fsub. Figure shows these two dependencies in graphical notation. With register renaming, it is a simple matter to resolve WAR antidependence between the second fadd and fsub. As mentioned, let XM be the program invisible register to which R2 has been mapped when the first fadd executes. This is then the remapped register to which the second fadd refers for its first data operand. Let fsub write its output to a program invisible register other than xm, which we denote by xn. Instructions which use the value written by fsub refers to xn, while instruction which use value written by first fadd refers to xm. The WAR dependence between the second fadd and fsub is removed, but RAW dependence between two fadd instruction is respected via XM. When the first fadd commits, the value xm is transferred to R2 and program invisible register xm is freed up. Likewise, later when fsub commits, the value is in xn is transferred to R2 and program invisible register xm is freed up. In the IBM 360 family of computer system of 1960s and 1970s, Model 360/91 was developed as a high-performance system for scientific and engineering applications, which involve intensive floating point computations. The processor in this system was designed with multiple floating point units and it made use of an innovative algorithm for the efficient use of these units. The algorithm was based on operand forwarding over a common data bus with tags to identify source of the data values sent over the bus. The algorithm has since become known as Tomasulo's algorithm, after the name of its chief designer. What we now understand as register renaming was also an implicit part of the original algorithm. Recall that for register renaming, we need a set of program invisible registers to which programmable registers are remapped. Tomasulo's algorithm requires these program-invisible registers to be provided with reservation stations of functional units. Let us assume that the functional units are internally pipelined and can complete one operation in every clock cycle. Therefore, each functional unit can initiate one operation in every clock cycle, provided, of course, that a reservation station of the unit is ready with required input operand value or values. Note that the exact depth of this functional unit pipeline does not concern us for the present. Figure shows such a functional unit connected to the common database with three reservation stations provided on it. The various fields making up a typical reservation station are shown as follows. OP, operation to be carried out by functional unit. Operand 1 and operand 2 are the two operand values needed for the operation. T1 and T2, two source tags associated with the operands. When the needed operand value or values are available in the reservation station, the functional unit can initiate the required operation in the next clock cycle. At the time of instruction issue, the reservation station is filled out with the operation code. If an operand value is available, for example in programmable register, it is transferred to the corresponding source operand field in the reservation station. However, if the operand value is not available at the time of issue, the corresponding source tag T1 and or T2 is copied into the reservation station. The source tag identifies the source of the required operand. As soon as required operand value is available at its source, which would be typically the output of a functional unit, the data value is forwarded over the common databus along with the source tag. This value is copied into all the reservation station operand slots which have the matching tag. Thus, operand forwarding is achieved here with the use of tags. All the destinations which require a data value receive it in the same clock cycle over the common data bus by matching their stored operand tags with the source tag sent out over the bus. Assume that instruction I1 is to write its result into R4 and that two subsequent instructions I2 and I3 are to read, that is, make use of that result value. Thus, instructions I2 and I3 are truly data dependent, RAW dependent on instruction I1. See the figure I2 and I3. Assume that the value in R4 is not available when I2 and I3 are issued. The reason could be, for example, that one of the operands needed for I1 is itself not available. Thus, we assume that I1 has not even started executing when I2 and I3 are issued. When I2 and I3 are issued, they are parked in reservation station of the appropriate functional units. Since the required result value from I1 is not available, these reservation station entries of I2 and I3 get source tag corresponding to the output of I1, that is, output of the functional unit is performing the operation of I1. When the result of I1 becomes available at its functional unit, it is sent over the common data bus along with the tag value of its source, that is, output of functional unit. At this time, programmable register R4 as well as reservation station assigned to I2 and I3 have the matching source tag. Since they are waiting for the same result value which is being computed by I1. When the tag sent over the common data bus matches the tag in any destination, the data value on the bus is copied from the bus into the destination. The copy occurs at the same time into all the destinations which require that data value. Thus, R4 as well as the two reservation stations holding I2 and I3 receive the required data value, which has been computed by I1 at the same time over the common data bus. Thus, through the use of source tags and common data bus, in one clock cycle, three destination registers receive the value produced by I1, programmable register R4, and the operand registers in the reservation stations assigned to I2 and I3. Let us assume that at this point the second operands of I2 and I3 are already available within their corresponding reservation station. Then the operations corresponding to I2 and I3 can begin in parallel as soon as the result of I1 becomes available. Since we have assumed here that I2 and I2 execute on two separate functional units. Let us now consider a combination of RAW and WAR dependencies. Assume that instruction I1 is to write its result into R4, a subsequent instruction I2 is to read that result value, and a later subsequent instruction I3 is then to write its result into R4. Thus, instruction I2 is truly data dependent on instruction I1, but I3 is anti-dependent on I2. About 15% to 20% of instructions in a typical program are branch and jump instructions, including procedure returns. Therefore, if hardware resources are to be fully utilized in a superscalar processor, the processor must start working on instructions beyond a branch even before the branch instruction itself has completed. This is only possible through some form of branch prediction. To understand this, we consider first reasoning which is involved if one wishes to predict the result of a tossed coin. A basic branch prediction technique uses a so-called 2-bit predictor. A 2-bit counter is maintained for every conditional branch instruction in the program. The 2-bit counter has four possible states. These four states and the possible transitions between these states are shown in the diagram. When the counter state is 0 or 1, the respective branch is predicted as taken. When the counter state is 2 or 3, the branch is predicted as not taken. When the conditional branch instruction is executed and the actual branch outcome is known, the state of the respective 2-bit counter is changed as shown in the figure using solid and broken line arrows. When two successive predictions come out wrong, the prediction is changed from branch taken to branch not taken and vice versa. In figure 12.14, state transition made on mispredictions are shown using broken line arrows, while solid line arrow show state transitions made on predictions which come out right. This scheme uses a 2-bit counter for every conditional branch, and there are many conditional branches in the program. Overall, therefore, this branch prediction logic needs a few kilobytes or more of fast memory. One possible organization for this branch prediction memory is in the form of an array which is indexed by low order bits of the instruction address. If 12 low-order bits are used to define the array index, for example, when the number of entries in the array is 4096, to be effective, branch prediction should be carried out as early as possible in the instruction pipeline. As soon as a conditional branch instruction is decoded, branch prediction logic should predict whether the branch is taken. Accordingly, the next instruction address should be taken either as branch target address or sequentially next address in the program. Technology is about trade-offs, and therefore it will come as no surprise to the student to learn that there are practical limits on the amount of instruction level parallelism which can be exploited in a single executing instruction stream. To achieve their goals, the processor designers make use of extensive software simulations of the processor using various benchmark programs within the target range of applications. The designer's own experience and insights supplement the simulation results in the process of generating solution to the actual problems of the processor design. Thread level parallelism. One way to reduce the burden of dependencies is to combine with hardware support within the processor instructions from multiple dependent threads of execution. Such hardware support for multi-threading would provide the processor with a pool of instructions in various stages of execution which have a relatively smaller number of dependencies amongst them, since the threads are independent of one another. Let us consider once again the processor with instruction pipeline of depth 8 and with targeted superscalar performance of 4 instructions completed in every clock cycle. Now suppose that these instructions come from 4 independent threads of execution. Then on average the number of instructions in the processor at any one time from one thread would be 4 into 8 by 4, that is equal to 8. With the threads being independent of one another, there is a smaller total number of data dependencies amongst the instructions in the processor. Further, with control dependencies also being separated into 4 threads, less aggressive branch prediction is needed. Another major benefit of such hardware-supported multithreading is that pipeline stalls are very effectively utilized. If one thread results into a pipeline stall for access to main memory, say, then another thread makes use of the corresponding processor clock cycle which would otherwise be wasted. Thus, hardware support for multithreading becomes an important latency hiding technique. To provide support for multithreading, the processor must be designed to switch between threads either on occurrence of a pipeline stall or in a round-robin manner. As in the case of the operating system, switching between running processes, in this case, the hardware context of a thread within the processor must be preserved. Depending on the specific strategy adopted for switching between threads, hardware support for multithreading may be classified as one of the following. First one, coarse-grain multithreading. It refers to switching between threads only on the occurrence of a major pipeline stall, which may be caused by, say, access to main memory with latencies of the order of 100 processor clock cycles. Second one, fine-grain multithreading. It refers to switching between threads on the occurrence of any pipeline stall which may be caused by, say, L1 cache miss. But this term would also apply to design in which processor clock cycles are regularly being shared amongst executing threads, even in the absence of a pipeline stall. Third, simultaneous multithreading. It refers to machine instructions from two threads being issued in parallel in each processor clock cycle. This would correspond to multiple issue processor where the multiple instructions issued in a clock cycle come from an equal number of independent execution threads. Thank you.